My name is Kedar Rao. This is Lab 9, the Physics of Extreme Sports with Ropes 2. I'm in lab section M03. The main objective of this lab is to examine the motion of a spring mass system in which the mass swings in an arc while oscillating on the spring. We can understand and predict this motion by using the momentum principle and the energy principle. The main result of this lab is that the period relative to the x-axis is 1.62 seconds and relative to the y-axis is 1.52 seconds. The spring potential energy is found to be 1.4 joules. So we use a model given to us from OSINE for our lab report. I'm not going to run it for you because it takes too long, but at the end, we plotted these points right here, and we found two graphs, mass of A, T, the time with respect to X, and the time with respect to Y. I found the period for the X by finding this point, the time is 3.05, subtracting this point 1.43 from that to find the period for the X. For the Y, I found the period by finding the time right here, 3.62, and subtracting 2.10 seconds from that. The initial conditions for this lab is that the mass of the ball is 0.402 kilograms, and the initial position of the ball is right here, negative 0.109, comma, negative 0.638, comma, 0. The initial velocity of the ball, or the mass, is 0, 0, 0. We found Ks to be 6.87, and the initial length of the spring to be 0.12723. I found the potential energy by multiplying the height, the ball position dot y, the magnitude of gravity, and the mass of the ball. Found kinetic energy by the formula 1/2 times the mass of the ball times the magnitude of the ball's velocity squared. I found the spring potential energy by the formula 1/2 times k times the magnitude of S squared. And I found S by subtracting the initial length from the magnitude of the final length and multiplying that by the unit vector for the length. I found delta t by multiplying 10.5 times 20. This gave us 1 over 210. 10.5 is the frames per second, and we did this 20 times, so 20 times 10.5. I did while t is less than 8.45 at a rate of 1,000. To find the force of the spring, I found S, which is magnitude of the length minus the initial length times L hat. And I did negative Ks times S. The net force in this module is the force of the spring plus the force of gravity. Updated ball position by multiplying the delta t times ball dot velocity and adding that to the initial ball position. To find the change in spring potential energy, I subtracted the initial spring potential energy from the final spring potential energy, and I found delta E to be the change in kinetic energy plus a change in gravitational energy, potential energy, plus a change in spring potential energy. Now let's take a look at the graph of the code. Here we plotted the change in total energy and the change in the spring potential energy. The red line is the change in spring potential energy, and the green line is the change in energy. And you can tell that this is correct because delta E should be 0 because energy is conserved. This is the law of first law of thermodynamics. You can see the x values and the y values related to time for the simulated model and the not simulated model. Because you can see that they're very similar. What does it mean? Question. The gravity is in the y direction. It's negative 9.81 in the y direction. So it affects the y component of the position more than the x component of the position, which is why the periods for x and y are two different numbers. The energy principle, the change in the energy is equal to the work. And in this case, the work is 0 because the system includes everything, and so the surroundings are 0. So the change in kinetic energy plus the change in gravitational potential energy plus the change in spring potential energy is 0. Last what does it mean question, we changed the length, the initial starting position of the module, and it is shown right here that the energies do not change. Thank you for your time.